Suppose there is a random point x comma y that you don't get to see. The game is prediction. I will look at the point, I'll tell you x, and you have to predict y. Then the conditional expectation of y given x is a natural function to use for prediction. And that's the function that has been graphed here. So supposing this is the graph of that conditional expectation. Then if I tell you that your point is at x, then the y can be anywhere on this vertical strip. This height here is the expectation of y given x. And what we're going to do is to see how good or bad this is as an estimate. So naturally, we want to look at the error. So let's write a few things down. Now, the conditional expectation given x is a function of x. So I'm just going to give it a short name. I chose B for best because I know the end of the story. But we'll see that this is a pretty good predictor of y under certain criteria. So then the error is the vertical distance between y and the conditional expectation curve. And I'm going to call this D for deviation with a W subscript. That is very commonly used statistical terminology. That is W for within. That is a deviation within a vertical strip. You know that all the points, the point xy could be anywhere here. The conditional expectation curve is fixed as just whatever function it is of capital X. But the deviation could be anything depending on where capital Y happens to be on that vertical strip. So D sub little w for within is the amount of error. And so why don't we look at some properties of this error? And one of the things you will see is that if we look at its expectation, and why don't we look at its expectation conditional on x? Now we'll calculate that, but it's going to be very important to understand what is meant by conditional on x in terms of the picture. So every time you see a condition on x, what you're saying is that I am working within this vertical strip. So what I'm saying is, what is the average of those errors within that strip? Now, these are deviations from the center of the strip, and so this better be 0. Let's take a look. Additivity. All right, now I'm going to take the expectation of y given x. Given x. Now, that, just by my notation, is this quantity. Bx is already a function of x. Once you are given x, you can treat x as a constant. After all, you're given it. And so that expectation is just itself, which is bx minus bx. No big surprise, if you treat that vertical strip as its own little distribution, that is the conditional distribution of y given x, then deviations from expectation average out to 0, just as any deviations from expectation do. And now by iteration, the overall expectation of these vertical deviations is 0. Let's write the math out first, and then we'll look at the picture. So the math is and the picture is, when you condition on x, you are working only on the vertical strip at x. But when you don't condition, then you are working across the entire range of x. So you are looking at this deviation and this one and this one and that one, and so on. You're looking at all possible deviations. And what we're saying here is that all of those deviations, we just average the whole lot, and then you get 0. No surprise there either. This leads to the most important property, which is the relation between this error and functions of x. This expected product is 0. Let's just establish that fact, and then we'll see what it implies. So what we're going to do is calculate the expected product by conditioning on x. Iteration. Now, g of x is a function of x, so it comes out of the conditional expectation inside. And we just showed that this quantity, the expected deviation within one strip, is 0. So the entirety, we are taking the expectation of something times 0, and we're going to get 0. Okay, well, that looks like a cute enough calculation, but so what? This means that the error and this arbitrary function of x are uncorrelated. And to show that, we just need to show that the covariance is 0. So covariance since we've calculated the expected product, We just showed that is 0. We also showed that is 0. So the error and functions of x, any functions of x, is uncorrelated. So this vertical distance from the point to the conditional expectation curve is a very, very interesting quantity. And the best way to understand this now is to forget about this diagram, which is on the xy coordinates, but to rather use your imagination and imagine the space of all functions of x. And I'm going to draw them as this flat surface here. And you should think of them as the surface of your table. Okay, and before I talk about y, remember all functions of x include x. They include x squared, log x, all linear functions, or any complicated function. They also include constants because those are also functions of x. And now y is not necessarily a function of x, so it does not necessarily live on that restricted plane. So it may live somewhere else. So that's a point that lives out there. And what we have said is that this error, the deviation of y from the conditional expectation, is uncorrelated with all functions of x. And geometrically, what that means is that the conditional expectation is the foot of the perpendicular that you drop from y to this plane. And there is your error. Uncorrelated for random variables should be understood geometrically as orthogonal as far as vectors are concerned. And that geometric intuition, I hope, will develop over the next little while. And if it doesn't help you, then don't use it. But you will see the conditional expectation of y given x called the projection of y to the space of functions of x. And we will soon see that if you use a particular criteria of what makes a good prediction, then this conditional expectation is the best prediction that you can make.